I mean, you probably aren't going to have fun.
Oh, thanks.
You're welcome. Because we're going to go back to one of our favorite things of all time, where you have to show that one side is equal to the other side. Remember those?
Oh,
The verifying the random trig identities. So this is actually the next page in your packet. I have 5 examples we're going to work through. And then after those 5, I have some for you to practice.
Okay.
All right. We're going to do notes slightly different because I am done standing. I don't know if y'all know that, but I think I'm finished with the standing. So I'm going to use the document camera and get it all set up and zoom in so you can see, even those of you in the back. If you can't see, just holler at me. We will make this happen, right? So we'll be on page 11.
Okay.
And you do not need a calculator, but you definitely want your orange sheet. And I even have some pretty colors. All right, gentlemen in the back, can you see that? Yes or no?
Yes, you are.
Yes, are you good? Paris, you good? All right. Okay, so what we're going to do is we're going to use the sum and difference, double angle, half angle identities now to do some of these proofs, all right? So before, it was everything else on your orange sheet, right? You could do the reciprocals or the Pythagorean identities or the quotient identities, right? But now we're going to add the 3 identities that we've been working with for the past week or so. All right? All right, so the first one, we want to show that the sine of 3 pi minus x is equal to the sine of x. And that 3 pi minus x is, you can use a difference identity for that, can't you? All right, so the 3 pi minus x difference identity, and you can use it straight from your orange sheet. So your orange sheet says for sine, for the difference identity, that will be the sine of 3x, or sorry, 3 pi, cosine of x, and then because I have a minus, I'm going to also use a minus, right? And then cosine of 3 pi, and then sine of x. And that comes literally straight from the orange sheet, this difference, sum and difference identity, and I just used 3 pi and x, right? 3 pi x, 3 pi x.
Yep.
Is everybody okay with that?
Okay.
All right. So from here, we have to show that this is equal to the sine of x. So where would you like to go from here? Y'all are going to put me in the right direction.
I would say just jump on the identity of cosine of 3 pi.
Yeah, cosine of 3 pi is a number, yes?
Yes.
You can evaluate the cosine of 3 pi. So using your unit circle, 3 pi is the same as what number? Is pi, right?
Yes.
So pi and 3 pi are both over here. So the cosine would be -1 and the sine would be 0. So for the sine of 3 pi, you're going to plug in a 0. So that's 0 times cosine x. And then minus, and for the cosine of 3 pi, you're going to plug in a -1. So you can always do some evaluating if you need to. If you have sine, cosine, tangent of an actual angle, go ahead and evaluate those. All right, and what happens here? What's 0 times cosine of x?
Well, 0 times anything is just 0.
Yeah, that's 0. So that whole thing goes away right there in the front, right? Negative times -1.
Well, that'll be positive.
Positive, and 1 times the sine of x is just the sine of x. So after the evaluation there of the sine of 3 pi and the cosine of 3 pi, you get sine of x. All right, what do you think? Super crazy? Not yet, right? Nah. I started with an easy one, yes?
Yep.
All right, we're not going to go in order because they don't go in order of difficulty. So we're actually going to jump to number 3 now.
Okay.
So taking a look, number 3. Get it all set up here. So this is the cosecant of 2x, and we have to show that that's equal to cosecant over 2 cosine. And so which side are we going to work with? The cosecant of 2x or the fraction? I would work with the cosecant of 2x because that's a double angle, right?
Yes.
So we're going to use a double angle identity. So if you grab your orange sheet, double angle identities. The only problem here is we don't have cosecant, do we?
Nope, we do a sine.
But we have sine, and cosecant and sine are
Reciprocal.
reciprocals. So whether that's just the cosecant of x or the cosecant of 2x, it can be written as the reciprocal, 1 over the sine. And since it's 2x on the inside, it's 2x on the inside of the sine. So 1 over sine of 2x. And then this denominator right here is where you can use the identity, right?
Mm-hmm.
So we're going to replace the sine of 2x with 2 sine of x cosine x. So just replace it. So this will be 1 over 2 sine of x cosine x.
Okay.
And then always remember where we're trying to get. So remember we're trying to get to here.
Uh-huh.
Cosecant over 2 cosine. Well, the next thing is I have the 2 and I have the cosine, but I need a cosecant.
Hmm.
So what can happen to make a cosecant?
Making sine
So cosecant is the reciprocal of
sine.
sine. So that sine moves to the numerator and becomes a
Cosine.
cosecant. So it's cosecant of x and then left in the denominator 2 cosine of x. All right, how are we doing so far? 2 down, doing good?
Okay.
All right. Well, we're going to make these a little bit harder.
That's a lot.
Let's go number 4 next.
Okay.
So on number 4, this one's a little tricky because you have a cosine of 4x and a cosine squared, sine squared. Both of those have 2 x's in them, right?
Mm-hmm.
So I am aware that technically that is this cosine identity, right?
Yeah.
Just regular cosine identity. So I don't want you to use this. I want you to show me that this is true by going a different way, all right?
Mm-hmm.
So would you rather work with the cosine squared sine squared or the cosine of 4x? Which side is the most complicated?
The cosine squared.
We would think it's the cosine squared sine squared, right, is the most complicated. But technically those angles are only 2x's, aren't they?
Mm-hmm.
The other side has an angle that's a
What?
4x. And that actually makes it slightly more complicated because that angle is bigger, right? Bigger angle. So I would actually suggest working with the cosine of 4x side.
Hmm.
It seems simpler, but to go from 2x's to 4x's is actually harder than to go from a 4x down to a 2x. And so cosine of 4x, we need to think about that differently. The cosine of 4x can be written as the cosine of 2 things added together. What 2 things could you add together? 2x plus 2x. That'll give us cosine of 4x, won't it?
Mm-hmm.
Now the benefit there is we have now changed it to a sum identity, haven't we?
Mm-hmm.
Yeah, so we're going to use the cosine sum formula, and we're going to set it up just like this, all right? So it'll be cosine of 2x times the cosine of 2x, because the 2 angles are the same. And then because of the plus, we'll actually have a minus, and this will be sine 2x times another sine of 2x. All right, and I think we're pretty much there. Cosine of 2x times the cosine of 2x is technically a cosine squared of 2x, because you're multiplying it by itself, right? And the sine of 2x times the sine of 2x is the sine squared of 2x. And that is what we have on the other side of our equal sign, so we know we are good. So if you ever wonder where that double angle identity right here comes from, it comes from using a Sum and difference identity. So a little bit more complicated there, I would say, just a little bit. All right, any questions so far? All right, we're going to keep rolling. We are going to move on to the hardest one now. That'll be number 2.
Okay.
Number 2 takes the cake for the hardest. All right, cosine of x plus y. This is times cosine of x minus y. We need to show it equals this. So which side should we work with, the left or the right?
I said that.
The left? Y'all agree the left? All right. And this is a multiplication problem, yes?
Yes.
So when I use the identity here, it all needs to go in parentheses because it needs to multiply, yes? All right, so let's go ahead and identity this cosine of x plus y.
The sum and difference.
So that would be, yes, sum and difference. So it would be cosine x, cosine y. The plus is going to mean that I have a subtraction sign. Sine x, sine y. And that is just the first one, right?
Correct.
Just the first one. So now I'm going to do the same thing with this second piece, and it also needs to go in its own set of parentheses. So this one will be cosine x, cosine y, and because of the minus here, we'll have a plus between them.
Good.
Sine x, sine y.
I'm guessing now distribute.
And yes, because of the multiplication, you technically have something minus something times something plus something, right? And so this would be like, for example, if it was like an x minus 2 and an x plus 2, you'd actually have to distribute that out, right? Now, before you just go crazy distributing, there is actually something fancy happening here on the multiplication. Anybody see it? It was a difference of squares, right? If I had to factor to get to this, it would have been a difference of squares because this and the beginning here are exactly the same, aren't they?
Correct.
And then this one and this one are exactly the same as well, but instead of them both being plus or both being minuses, they have opposite signs. So what's going to happen is those middle terms are going to make 0, aren't they?
Good.
Essentially, you can think about this as multiplying by the conjugate as well. So a difference of squares factoring is the same idea as multiplying by the conjugate. So some really nice things are going to happen when we multiply this out. So we'll have this first piece times itself here. So cosine of x cosine y times the cosine x cosine y. And you can multiply in any order. So cosine x would multiply to be cosine squared of x. And then the cosine y is cosine squared of y. And that'll be the first multiplication there. And then what'll happen here when we multiply the cosines by the sines, we'll get a positive. And when we multiply the sines by these cosines, we'll get a negative. And those will be the exact same terms, but they'll just have opposite signs. And so those will add up to be 0. So you don't even have to write them down. And then you do have to do this sine times the sines. So it'll be a negative times a positive, so these will be negative. Sine of x times the sine of x is sine squared of x. And sine y is sine squared of y.
Okay.
And there is a slight typo on this. I forgot to mention it. My bad. We'll fix it real fast. We don't have to change anything so far. In the what we're trying to get this equal, it's sine squared y, not sine squared x. That will make a slight difference. So change that real fast. Sorry. We didn't realize that with my second block, and we were doing it. I was like, "Why didn't we get what we were supposed to get?" And that was just a typo on my part. All right, I'm gonna pause. Any questions so far on that multiplication? There's a lot going on there in terms of the squaring, and then you have 2 terms that make 0. All right. If there's no questions, we'll press on. So let's take a look at what we have. We have cosine squared x, cosine squared y. sine squared x, sine squared y. Any thoughts here on what we should do? We need cosine squared x and minus sine squared y. Any thoughts? This is what makes this one a little tricky right here, for sure.
You use an identity?
You can use an identity, yes. So which identity shall we use? Because you have an entire page full of identities.
Sine
Yep.
squared plus cosine squared?
Yeah, use a Pythagorean identity, right? Now there's actually 4 places you could use the Pythagorean identity, isn't there? You could replace this, or this, or this one, or that one. So let's replace one and see what happens, and let's pick a one on purpose. All right, so let's not just pick a random one. So pick one to replace that we know we won't need. Cosine squared of y. You know you do not need a cosine squared of y because there's not one in the answer that you're trying to get to. So we are replacing this one here. The other one that you could replace would be the sine squared of x, because you know you don't need that either. All right, so cosine squared y gets replaced as 1 minus sine squared y. And there's a cosine squared of x in front of it, and then we have the sine squared x sine squared y behind it. Alrighty, where to from here?
You distribute the cosine of x?
Sure, let's try. So distribute the cosine of x, cosine squared. So cosine squared of x times 1 is just cosine squared x. And then times, so we'll have a minus cosine squared x sine squared y. And then I have this last term that hasn't changed. Sine squared x sine squared y.
And now do you do it to the other side?
Yeah, sine squared x.
Like the other side, like mess with this now? To try to get that?
Yeah.
You could. I don't know what you would mess with completely though. Because you need the cosine squared of x, right? And we have one of those.
So if you turn the sine squared of x into the 1 minus cosine squared of x, and then distribute that, then I think the 2 will cancel each other out, so it's just cosine squared of x minus sine squared of x.
All right, so you want to take this right here and change that into 1 minus cosine squared of x?
Yes.
And then technically there's a minus in front of that, right? From this minus?
Yeah.
And that would be times the sine squared of y? Like that?
Yeah.
Does everybody see what he's doing there?
Yes.
All right. And so I'm going to go ahead and distribute this before I write the rest of it down. So this would be a negative 1 being distributed, so that would be a minus sine squared y. And then this would be a negative negative, so a plus cosine squared x sine squared y. Just on this last piece here. And then you can take all of this and just bring it down, right? Cosine squared x minus cosine squared x sine squared y. All right, did it work?
Yeah.
It did, didn't it? Because this term here and this term here are the same terms with opposite signs. And so we're left with just cosine squared of x minus sine squared of y. There you go. You could have done one thing slightly different here on this step in like light blue, right here, this one I'm pointing to.
Okay.
Instead of changing the sine squared of x to get to here, you could have noticed that this term and this term both had a sine squared of y. And you could have actually factored out the negative sine squared of y. You see how they both have them? And they both have negatives? And if you take that out, you would have had cosine squared x plus sine squared x, which is 1. So then it would have been negative sine squared y times 1, which is just negative sine squared y. So that would have maybe made that slightly easier if you saw it, but if you didn't see it, the diagram identity worked as well. Definitely a lot more going on with this one, huh? Yes, for sure. A lot more complicated. Really, the fact that there's a multiplication here made it a lot more complicated because we had to really work through that multiplication. Fun, right?
Sure.
So fun. I told you you're going to have fun today.
Uh-huh.
All right, what other questions? Do you have any other questions about this one? So some of them might be pretty easy, right? Like 1, 3, 4, those weren't super bad. This one, definitely a lot harder, yes?
Yeah.
All right, we're going to do one more together, and that is number 5.
Okay.
Number 5 has a little disclaimer, though. I'm not going to put any with half angles on the test. So if you're asked to verify, you don't have to use any half angle identities to verify, all right? Sound good?
Okay.
All right. So we're going to prove that this is equal to this. Or at least we're going to try.
Well,
Sorry, I'm still getting this set up. For some reason it's spinning. Hold on. All right. Got it. Take 30. Hey, there we go. Okay. So this is where the half angle lives, right? X over 2. So you can use a half angle formula, yes?
yes.
Now the problem is we have secant,
Yeah.
but we don't have secant.
So I get you the cos.
So you can use cosine, but you have to do
Reciprocal.
the reciprocal, right? 1 over. So you can say that secant is 1 over the cosine of x over 2. And then you can replace this denominator with your identity here. You do not need to worry about the plus or minus if you're trying to just identity prove things, all right?
Okay.
No worries there. So we'll just go with the plus. So 1 over, and then you have that whole square root in the bottom. Cosine of x all over 2. All right, and here's why I'm going to not keep half angles on the test. Where do we go from here? Huh?
Imaginary?
You don't have to go to the imaginaries, no.
Huh.
Because the cosine of x, if you think about the graph, what's the biggest number for the cosine of x?
1.
1, and if you do 1 plus 1 over 2, that's a positive number, right? And what's the smallest number for cosine?
Negative.
Negative 1, so it'd be 1 minus 1, which would be 0, right? And you can still square root 0. Now, it's undefined there because it was originally a secant, right? But that's why we don't have to go into imaginaries, because we never will take the square root of a negative number. Because cosine has a limit, top and bottom. Yep. So, good news, no imaginaries. Not that you can't do imaginary numbers with trig functions, because you sure can. And you probably will if you take math in the future. But not necessary at the moment. Not to scare you. It's not scary. Don't be scared.
Fine.
Not scary, it just sounds like a lot of work.
It's not too bad. Any thoughts, though?
Well, try, reverse almost, take it out from the bottom. Hmm. I think that's.
What would you do if there wasn't a square root there?
Oh, I was simply multiply by the.
Flip and multiply, right?
Oh, we can still do that
Why can we still do that?
because you can just put square root of 2 and then square root of 1 plus.
Oh, ooh, right. The square root, technically, when you square root a fraction, it's the square root of the top over the square root of the bottom.
Mm-hmm.
Yes? You want to roll that way and see what happens?
Sure.
Topaz shaking his head no, though. He's like, no, I don't want to go. I don't want to do it.
I don't want to do it at all, but I have to let's do it.
We're going to go for it. Let's see what happens. So this would be 1 over the square root of the top over the square root of the bottom. Yes?
Yeah, fine.
Now could you flip and multiply?
Yeah.
Yeah? So we would take this guy, right?
Mm-hmm.
And he would come up and be multiplied, and when we flip it, it'd be the square root of 2 over the square root of 1 plus cosine of x. And that all gets multiplied by 1. And if it all gets multiplied by 1, then you just have this, right?
Yeah.
All right, so we are currently sitting at square root of 2 over square root of 1 plus cosine x. That's our current location. Right here. I feel like we made progress with that.
Yeah, a little. That's nice.
Instead of having a fraction in a fraction, it's now just one fraction.
Yeah.
All right. So next step, what do you think? Where should we go from here?
Hmm.
You could rationalize it, but I'm not sure we want to.
So you could rationalize it by timesing the top and the bottom by 1 plus the square, or 1 plus cosine x. Why would you say I'm not sure we want to?
Because the other side is still in a square root.
Because what you're trying to get it equal to has one big square root, right?
Yeah.
So rationalizing the denominator wouldn't keep it all in a square root.
No.
Right. So yes, I think, yes, you could rationalize, but you definitely don't want to.
No. Hmm. Okay. Hmm. Yeah. Hmm. Can you
Multiply everything by tangent.
I'm going to say yes, but not yet.
Oh.
Because we certainly want, if you look where we're going, to have a 2 tangent, right?
Mm-hmm.
And you can easily change that 2 into a tangent by multiplying literally everything by tangent. And in the denominator, you need a tangent and a sine, and so you have a 1 and a cosine. If you times by tangent, that would be tangent and sine, right? So yes, but we can't do it yet because of those square roots.
So you just make it 1 square root.
Make it 1 square root. How can you make it 1 big square root?
I mean, all you
The opposite of what we did before.
Yeah, so right here, this step, you said take the square root of the top and the square root of the bottom, right? Remember it is 2 separate square roots? Well, if that applies to splitting it, it also applies for putting it back together, yeah. So from here, you can say 1 big square root, 2 on the top, 1 plus cosine of x on the bottom. You can most definitely do that.
Hmm.
So if it's a square root of the top and the square root of the bottom, technically it's a square root of the whole thing, right?
Yep.
All right. Now let's go with your idea, Colin. That was to do what?
Multiply everything by tangent.
Multiply everything by tangent. So technically you're timesing by tangent over tangent. And we can do that
Because it's 1.
because tangent over tangent is equal to 1, yes. So in my second block, they're like, one of the kids was like, we should just force a tangent in there. And technically that is what we're doing, right? We're forcing a tangent. Sorry, there we go. And that's because as long as you multiply by some form of 1, you can multiply by whatever you want to. Literally anything, okay? So this would be a square root. On the top would be 2 tangent of x. By the way, technically we're multiplying by the square root of this, right? To keep those in a square root,
Yeah.
technically. Or you can just think we're multiplying by tangent over tangent inside of the square root, right?
Yeah.
However you want to think about that. All right, so 2 tangent of x on the top. On the bottom, you have to distribute the tangent. So 1 times tangent is tangent of x. And then tangent times a cosine is technically just a sine, because tangent, sine over cosine, times cosine means the cosines would simplify, leaving you with just a sine. Nice work.
Fine.
What'd you think? Half angle identity, yeah? Ew.
So much fun.
So much fun. By the way, my second block, they did it slightly different. When we got to this point here, they what we did was we changed the top into the 1. You could say 1 is the square root of 1, right? And then that means that you could put it in one big square root from the get-go. And then they just flipped and multiplied on the inside and just worked with the inside. So you guys flipped and multiplied while you still had multiple square roots, and then square rooted the whole thing at the end, like turned it into one big one towards the end. And they did this piece, but they did it over here.
Oh, so
Yeah.
no much difference.
Yeah, so not much different. They just did it in a different, slightly different order. But as long as you obey all the rules of algebra, right, then you are good. All right, that is all I have for you in terms of notes. And so I'm just going to give you some time to practice. So on the back, there are 6 of them. And just be careful with some signs and some things like that. Some of them actually come a lot faster in terms of like getting to where you're supposed to get to. So they might look intimidating, but you end up with the answer a lot quicker than you would expect, all right? I do have all the solutions. You can check your work. And by check your work, you can let me know what I can do to help, all right? All right.